Okay, we're going to look at finance examples next. We'll start by building a mathematical model that describes the amount of money inside a portfolio, amount of money inside an account. In this particular problem, we're starting with $0 in the account, but it's an account with an awesome interest rate, 100% compounded continuously. It's amazing, unbeatable. Now, at the end of every year, we're going to throw $200 into this account. And I want to write down a mathematical model that describes how much money is in here. There's a few pieces of vocabulary that we have to get used to when we work with finance applications. One of them is, what does percent mean? Percent literally means out of 100, per cent, French, out of 100. So if you see 100%, and you want to incorporate that number into a calculation, you need to divide it by 100. So R equals 100% is equal to 100 divided by 100, which is equal to 1. If it was 50%, it'd be 50 out of 100, which is 0.5. If it was 10%, it'd be 10 over 100, which is 0.1. You always need to convert your percents into decimals in order to incorporate them into a formula like this. Don't get thrown by the continuous compounding. If you've already learned some finance previously and you've learned the distinction between continuous compounding and discrete compounding, don't panic. We're not going to do anything except continuous compounding inside this course, which is generally treated as an approximation for discrete compounding anyway. All right, so let's write down this mathematical model, which will have two components. It'll have the initial condition, which is usually easy. That's how much money do we start with. So y of 0 is equal to 0. That's our starting money. That was given to us in the question. And then if you think about this pile of money, it's growing in two different ways. In one way, it's growing according to the interest rate that's applying to it. And interest rate growth is like the birth rate in the population. I'm going to let y equal amount of money in an account. At time t. It's a function of time. And t is in years. Okay, so dy by dt is equal to, for populations, larger, if you have 10 times the population, you have 10 times as many babies. For bank accounts, if you have 10 times as much money in the bank account and it's a constant interest rate, then you're going to have 10 times as much money growth. You're going to have, if it's a $100 account compared to a $1,000 account, if the $100 account grows by $2, the $1,000 account is going to grow by $20. So it scales in proportion to how much is there. So we would write that as R times Y, so the interest rate times Y, plus a term that we did not talk about in our population models. This is a term of, in a population models, a migration term. So for a bank account, it's a deposit term. So plus 200 from our deposits. Now I'm going to convert this R into a 1 times Y plus 200. So R times Y, that was the interest growth. And the 200 is the deposit term. And the next step, we're going to solve the mathematical model. This is a nice differential equation. It's one that can be solved both as linear first order or as separable. I'm going to solve it as a separable differential equation. I'm going to divide both sides by y plus 200 and multiply both sides by dt to separate the variables. Separate the y stuff on one side, the t stuff on the other side. And then integrate both sides. The antiderivative of 1 over y plus 200 with respect to y is ln of y plus 200. The antiderivative of 1 is t, and then I'll throw in that constant of integration that we always get. Next, let's solve for c. Using y of 0 is equal to 0. So ln of 0 plus 200 is equal to 0 plus c. So ln of 200 is equal to c. Okay, we're not quite done building our model. I want to get y all by itself. We're almost there. We have the ln of y plus 200 is equal to t plus the ln of 200. So I'm going to exponentiate, raise both sides as powers on a base of e. E to ln of y plus 200 is equal to e to the t plus the ln of 200. I get a cancellation law on the left. Y plus 200 is equal to e to the t times e to the ln of 200. I get a cancellation law there. So y plus 200 is equal to 200 e to the t. Thus, y is equal to negative 200 plus 200 e to the t. There's our answer. You can make a graph of that, see what it looks like, but it's this exponential growth curve. I'll draw it on the slide here and then erase it. It looks like this. It has that exponential growth shape, and it's the compounding that's causing that shape to happen. So we could use this mathematical model then to determine how long it would take to reach $100,000. So we found y is equal to negative 200 plus 200 e to the t. So we have 100,000 is equal to negative 200 plus 200 e to the t. And add 200 to both sides, so 100,200 is equal to 200 e to the t. Divide both sides by 200. And then cancel. I can cancel the zeros. I have 1,002 divided by 2, so 501 is equal to e to the t. And then ln both sides. And we can make a conclusion for this. Thus, t is equal to the ln of 501. But what's that? I'm going to plug in my calculator. Oh, some emails. It's 2 a.m. I'm not answering emails at 2 a.m. Ln of 501, 6.22 years. And this is a very different answer than what we would get if it was discrete compounding. If it was annual or monthly compounding, we would get a longer time period. So if it's 100% every year, just under 8 years, I think, compared to the continuous compounding time of 6.22 years. But it's pretty amazing that if there was such an account with 100% interest rate, I mean, getting from throwing in $200 a year, getting up to $100,000 in either 6 years or 8 years, doesn't matter. They're both fantastic. It's just that 100% interest rate isn't realistic. What happens if we make the numbers more realistic? Well, first of all, they become harder to work with, but second of all, our models will look more reasonable. They'll look like what you might hear people talking about when they talk about savings, when they talk about debt and mortgages and car loans and all that stuff. It'll sound more familiar than this is patently ridiculous. So this investment portfolio currently has $500 in it, a constant effective interest rate of 5% compounded continuously, and then at the end of every year, $200 more is tossed in as a term deposit. We want to first write down the mathematical model that will describe the rate of change of the amount of money in the portfolio, and then solve the mathematical model. So this one's going to be ugly. There's going to be some either decimals or fractions, I think I'm going to use both decimals and fractions and kind of switch in between them depending on what's most convenient at any given time. Okay, so big picture, we want our model, which is going to have two components. The first component, which is almost free, is our initial condition. How much money are we starting with? Y of 0. That's equal to 500. That's our starting cash. Starting cash. And 500, and then the differential equation, dy by dt, is equal to our interest term, y, or r times y, plus our deposit term. So our interest term, r is equal to 5 out of 100, which is 1 over 20, or 0.05. So if you like decimals, convert to 0.05. If you like fractions, leave it as 1 out of 20. I'll put 1 over 20. I hate decimals and I hate fractions. Just can't decide which one I hate least. 1 over 20y plus 200. So that's our dy by dt. That's the rate of change of the amount of money in the account. And our initial condition, y of 0 is equal to 500. You put them together, that describes the mathematical model. Part B, we're going to solve the mathematical model using a similar process to the last problem. This is a separable differential equation. It's also linear first order. I'll solve it as a separable. So dy by dt is equal to 1 over 20y plus 200. I'm going to multiply everything by 20 to get rid of the fraction, right? Because we hate fractions. I think everyone hates fractions. $4,000, right? Multiply by 2, you get 400. Multiply by 10, you get 4,000. All right, and now I'm going to divide both sides by y plus 4,000. So 20 dy over y plus 4,000 is equal to 1 times dt, and then integrate both sides. Little trick, right, for not having fractions everywhere, or having decimals everywhere. Okay, antiderivative of y plus 4,000 ln of y plus 4,000. We have a 20 in front. 20 ln y plus 4,000 is equal to t plus c. Now we're going to find c. Find c from y of 0 is equal to 500. So 20 times the ln of 500 plus 4,000 is equal to 0 plus c. So 20 ln 4,500 is equal to c. Thus, 20 times the ln of y plus 4,000 is equal to t plus 20 times the ln of 4,500. Let's see, I want to get the y all by itself, so I'm going to divide everything by 20. So ln of y plus 4,000 is equal to 1 over 20 times t plus the ln of 4,500. And we're going to run out of space, so I'm going to go to the next slide. So ln y plus 4,000 is equal to 1 over 20 times t, and I can't remember the other number, ln of 4,500 plus the ln of 4,500. Now I'm going to exponentiate, raise both sides as powers on a base of e. So e to the ln of y plus 4,000 is equal to e to the 120t plus ln 4,500. Both of those things on the right are in the same exponent. Cancellation law over there, y plus 4,000 is equal to e to the 1 over 20 times t times e to the ln of 4,500. We can cancel that one. So y is equal to negative 4,000 plus 4,500 times e to the 1 over 20 times t, or if you like decimals better, negative 4,000 plus 4,500 e to the 0.05 t. Now what I invite any of you to do, if you were uncomfortable with this step in here, multiplying by the 20, or this step over here, going from 5 over 100 to 1 over 20, instead of just immediately like punching into a calculator and getting your 0.05, which is what I think high schools unfortunately are training people to do now, go through the calculation with your decimals and look at the disaster that gets created, and just, you know, a little bit of work at the beginning, just a little bit of work with this fraction. All we did was multiply all the pieces by 20. The decimals went away, the fractions went away. We had a little bit of mess, still a little bit of mess to work through, but it was not nearly as bad as what you will see if you try to keep the decimals in there. I'm going to circle both of these. They're both great. Okay, and then how long will this investment account take to reach $100,000? So we found y is equal to negative 4,000 plus 4,500 times e to the 1 over 20t. So this time I'm setting 100,000 equal to that. Okay, so 104,000 equals 4,500 times e to the 1 over 20t. Divide both sides by 4,500. We can get rid of the double zeros in the end. Cancel double zeros top and bottom. Then we can divide out a 5, I guess, but let's not do that. We're starting to get into the silly territory. We can ln both sides. So ln of 1040 over 45 is 1 over 20 times t. Thus, t is equal to 20 times the ln of 1040 over 45. And calculator, 62.8 years. And that's more realistic. Now we have a $500 account. We're throwing $200 a year into it. It's getting hit with a 5% interest rate. It is going to take a long time to get to $100,000, 62, almost 63 years. And that's with continuous compounding. With discrete compounding, it's going to take even longer. There's a moral to the story. You need higher interest rate, or you need to throw more money into the account to get to that high of a savings target. Okay, another example. An investment portfolio currently has $1,000 in it. Constant annual effective interest rate of 6% compounded continuously. At the end of every year t, an additional $200 is invested into the account. So every year, it's not a constant amount of money. The amount of money that's being deposited is increasing. So in the first year, they throw $200 on top, whatever is in there. And then the second year, they throw $400, 200 times 2, and then $600 and $800. what mathematical model. So this doesn't want us to solve the entire thing, it just wants the model. So the easiest part of the model is the initial condition. How much money is in there initially? Y of 0 is equal to 1,000. Initial amount of money. And the rest is the differential equation. dy by dt is equal to r times y plus the deposit term. So r is 6%, so we have 0.06. 6% is equal to 6 over 100, which is equal to, divide top and bottom by 2, 3 over 50, or 0.06. So I'll put 0.06 y plus the deposit term, 200t. That's it. That's the answer. We have our interest growth. And we have our deposit. How would we solve this? We must solve using linear first order method, which is with integrating factors. But the question doesn't ask us to solve it, it just asks for the model. And that's what we've done. I put a visualization together so you can compare these types of investment schemes with compounding, without compounding, constant deposits, deposits that grow with time, just throwing money under a mattress every month and not having it exposed to a compounding interest rate. Let's see, they're all there. You can click this Desmos link and it'll take you to explore the curves. If you take this curve that's there and you click the link, you can zoom out and you can see that two of these curves will eventually cross, and you can decide for yourself what that means. You can also play around with the slider bars at the top. So change the initial amount of money in the account. That's the A value. Change the interest rate. Right now it's 6%. And see what happens if you bump it up to 8. And then look at the deposit parameter, $500 annual deposit being thrown into the account. See what happens if you tune that number. So play with the numbers to see how those graphs change. How sensitive is one graph to a change in one of the parameters? Or maybe some graphs are more sensitive to a parameter than another graph. But the vertical line there is the 30-year mark. So it's comparing the outputs of the different models after 30 years. So I'll just highlight something here that this initial investment plus yearly deposits that increase every year. So you have a 6% interest rate, you're throwing money in every year, and the amount that you throw in every year is growing with time. That's this top curve. And after 30 years, there's $457,000 in the account. There's half as much in the account that has the same amount of money being thrown in without any compounding. So this is just money being thrown under a mattress. Sorry, a different amount of money. It's a growing amount of money being thrown in, but there's no interest rate being applied to it. So this is saving more money each year, but just maybe throwing it into a pit under the ground, not investing it. And then the purple curve underneath is constant deposits being added to the account and an interest rate of 6%. So this is not saving a lot. This is a low savings. So you start with some money and you very slowly add to it. And after the 30-year period, there's $48,000 in there. Just because you haven't added enough for it to grow. These two curves, the purple curve and the dashed blue curve, eventually cross. What happens is at some point, 80 years or something, or maybe 90 years, I forget what it is, the compounding does become more important than the tossing in of additional money every month. That growth of the money being tossed in every month is growing linearly. It's a 200t or whatever it is, 500 times t. So it's a linear growth rate of the deposits, whereas the compounding is an exponential growth rate. And at some point, the exponential growth rate will take over. It'll dominate. Compounding wins in the end. No savings rate will beat compounding unless the savings rate is exponential. Or the growth of the savings rate is exponential. Okay, here's another one, another type of model. We have a pharmaceutical drug that's earning some amount of money per year, 14 minus 2t, millions of dollars per year. The money's put into an investment portfolio that earns 7% annual rate of return. Assume continuous compounding and initially $0 in the portfolio. Write down a mathematical model. All right. Something to note here is think about what's happening at different t values. If t is equal to 0, it's $14 million being earned. T is equal to 1, $12 million. T is equal to 2, $10 million. And eventually you get to 7 years, plug t is equal to 7, and 14 minus 2 times 7, 14 minus 14 is $0. So what this model is describing is a drug that has a shelf life, or maybe not shelf life is a bad term, but it has a marketable life of 7 years. Eventually it's going to be replaced, or its patent will run out, and it will no longer be able to be manufactured at profit by that company. It's just a model. Okay, so let's write down what that model is. Let's do the simple part first. The initial condition, how much money starts off in the account. Y of 0 is equal to 0. And now the differential equation, the rate of change of how much money is in the account, is equal to your interest rate, so R, times how much money is in the account, plus your deposit, plus 14 minus 2t. So that was your deposit term. That's what you're depositing. That's your earnings. That's your interest. And 0 is your initial. There's your model. And then part B, we're going to solve the mathematical model. And we have to solve this using integrating factors. There's no other way. Use integrating factors. It's not separable. It's not a product of a function of t and a function of y. So we can't separate the variables. dy by dt plus negative 0.07 y equals 14 minus 2t. So now it's in standard form for linear first order. Y prime plus p of x times y is equal to q of x. So negative 0.07 is our p of x. 14 minus 2t is our q of x. So we're going to obtain the integrating factor. To do that, we first integrate p of x. So the integral of negative 0.07. Oh, I guess it's p of t. It doesn't make any difference. But well, just to be consistent, negative 0.07 t. And then your integrating factor, I of x, is equal to e to the integral of p of, or I of t, there I go again, force of habit. So e to the negative 0.07 t. Or e to the negative 7 over 100t. If you don't like decimals. I'll just do that because I don't like decimals. Now, we have our integrating factor. What do? We have our big formula. Thus, y is equal to 1 over integrating factor times the integral of our integrating factor times q of t, dt. So 1 over e to the negative 7 over 100t times the integral of e to the negative 7 over 100 times t times 14 minus 2t dt. I'll have to continue this on the next slide because it's going to take more space. Okay, so just copy the previous line to the next slide. Okay, I'm going to clean this up a little bit. We can use exponent laws. We have 1 over e to a negative exponent. We could bring it up as e to a positive exponent upstairs. So e to the 7 over 100t times the integral of 14 e to the negative 7 over 100t minus 2t e to the negative 7 over 100t dt. And let's split those two integrals up. Let's integrate e to the negative 7 over 100t dt. So we'll use a substitution. W is equal to negative 7 over 100. Complete the substitution. What you'll find is that this is equal to negative 100 over 7. E to the negative 7 over 100 t plus c. The other one's harder. So integral of 2t times e to the negative 7 over 100t. This one needs integration by parts. So u is the algebraic term, is 2t. So du is equal to 2 dt. And dv is equal to e to the negative 7 over 100 t dt. So v is the integral of that, which we just found up above. We found the integral of that function. We get negative 100 over 7 e to the negative 7 over 100 t plus c. And that's going to get plugged into our IBP formula. Now, this is a nasty question, no doubt about it. Every piece of this was nasty. uv minus the integral of v du. But we've been using all the tools that we've learned. And this is a pretty realistic finance problem. So 2t times the dv term. So 2t times negative 100 over 7 e to the negative 7 over 100 t minus the integral of v du, negative 100 over 7 e to negative 7 over 100 t dt. And then we can clean this up a little bit. We get negative 200 over 7 times t times e to the negative 7 over 100 t. And then we get minus 100 squared over 7 squared e to the negative 7 over 100t plus c. Just using substitution with w equals negative 7 over 100 again. And we'll get a negative 100 over 7 that will come out and join the existing negative 100 over 7. And the existing additional minus sign. So we end up with we still end up with a negative. Okay, I'm going to plug all that stuff in up above. And hope no mistakes were made. Please scream at me if there are mistakes. Okay, so the first integral was also a 14 there. So 14 times negative 100 over 7 e to the negative 7 over 100 t. I'll add the plus c inside the box afterwards. And then minus what we got in the red. Negative 200 t over 7 e to the negative 7 over 100 t minus 100 squared over 7 squared times e to the negative 7 over 100t and then plus c. And then we can clean this up a little bit. And 14 over 7, 2, so negative 200 e to the negative 7 over 100 t plus yeah. Maybe it's better to negative 1,400 over 7, not simplify it, plus 200 over 7 e to the negative 7 over 100 t. Oh, there's a t there, 200t. Oh my god, there's so many pieces. And then plus 10,000 over 49 e to the negative 7 over 100 t plus c. And then we can collect like terms. So the first term of the brackets and the third term of the brackets are like terms. We make common denominators and combine them. We can also multiply the e to the 7 over 100t into the brackets. So I'll get, let's see, times 7 so that's 98, negative 9,800 over 49 plus 200t over 7 plus 10,000 over 49 plus c e to the 7 over 100t. So I multiply the e to the 7 over 100t into each term and use exponent laws. We have e to the x times e to the negative x, so e to the x minus x, so e to the 0. So this times this gave us 1. this times this gave us 1, this times this gave us 1, and this times this survived over here. Okay, let's collect those like terms. Negative 9,800 plus 10,000 is positive 200. So we get 200 over 49 plus 200t over 7 plus c e to the 7 over 100t. And then it says y of 0 is equal to 0. So 0 is equal to 200 over 49 plus 0 plus c e to the 0. So c is equal to negative 200 over 49. And we can make our glorious conclusion for the mathematical model that describes this account. Thus, y equals positive 200 over 49 plus 200t over 7 minus 200 over 49 e to the 7 over 100t. And I should add a little stipulation. This is for t less than, this is for t between 0 and 7. So 0 less than or equal to t less than or equal to 7. After 7, look what happens to the model. Again, we have 14 minus 2t. The deposits become withdraws, which breaks what we're trying to mathematically model. What's the value of the portfolio at time t is equal to 7? So we'll take that and plug that in. And get some number. Not important. There's probably a mistake in there anyway. So as a summary of the formulas that are important for finance applications, if we have an amount of money that's subject to a continuously compounded interest rate R, and we also throw in deposits, then the rate of change of our account is given by the derivative of the account, so dy by dt, and that's going to be equal to the interest rate R times how much money is in the account, so R times Y, plus your deposit term. And very often we would stop there with the initial condition with y of 0 part. That would be where we would stop. We just built the model. If we need to solve it and our deposit term is a function of time, then we would have to rewrite it as dy by dp plus negative r times y is equal to L of t. Our integrating factor, which we would get from this linear first order equation, is always going to be e to negative rt. And if you look at the example we just completed, this is what will always come out. Every single time we do one of these, our amount of money in the account is going to be e to the rt times the integral of e to negative rt times our deposit term. And you'll find this formula in some finance textbooks. And they'll say it can be derived using calculus, and that's what we just did. We just derived one of the important finance formulas using calculus. And I'll stop here and talk about other things you can do with differential equations in the next video.